Hi there, and welcome to YCP Chemistry Lab, your college's YouTube channel to help you get ready for lab each week in the general chemistry curriculum. I'm Dr. Bill Steele. I'm the coordinator of the laboratory curriculum. I've written the laboratory manual that you'll be using this semester in your General Chemistry 1 course. Each week I'll be preparing a video to get you ready for lab. So you'll see me here usually in front of the whiteboard. You should recognize this room by now as Campbell Hall 217. We're on the dry side of the lab. Off to my right, your left as you're watching, is the wet lab area where each week you'll be conducting the experiments written out in your laboratory manual. So this is our first pre-lab video and our first chance to get together to talk about how we prepare for lab each and every week. As hopefully you've seen by now, your lab manual has a sort of cream-colored page that's part of each procedure for the respective weeks of the experiments that we're doing. That's your pre-lab, and you should be completing the pre-lab questions before you come to lab. Usually as part of these videos, I'll provide you with some hints for those questions so that you can be sure you're getting the right answers when you come into lab each week and earning those points for conducting the pre-lab questions. But I'm also going to give you some hints and safety guidelines on the procedures for each week to get you ready to have a great experience in lab. So usually we'll start with an overview of the purpose and procedures that we're doing in lab, talk a little bit about the safety concerns, introduce any new equipment that you might not be familiar with, and then I'll review some of the concepts that you might need to answer the pre-lab questions, and that'll wrap it up. My goal is to try to have the pre-lab videos last between 10 and 15 minutes. Now, sometimes it might take a little bit longer, and other weeks we might be a little bit shorter. But I just want you to be prepared for what to expect each week. So this first week, we have a pretty straightforward exercise on tap. We're looking at the fundamentals of measurement. We're early in the semester right now, and we're learning how to use the tools of measurement. Be it in chemistry, in physics, or any other discipline, there are always tools that we use to conduct measurement. And there are rules for how we use those tools, and that's what today's experiment is all about. So you're going to have a few different tools at your disposal as part of today's work. And I'll show you those tools in a minute. We want to make sure we apply the correct rules to each of the respective tools. Then, after we measure some objects with those tools, we're going to be performing calculations with those measurements. There's, again, a correct set of rules for how we combine numbers. All of this relates to what we call the significant figures. Maybe you've heard that term introduced in your lecture by now. So we're trying to arrive at a calculated value with the correct number of significant figures. And finally, as always, we're going to want to consider the units of our answers. If our different tools have had different sets of units for measuring different things in the lab, what are the units of our answer? That's one of the final pieces of the puzzle that we have to explore. Right. So, as an overview, the general idea of significant figures are that you can report all of the known values of certainty, okay? Numbers that you are absolutely sure about from the scale you're looking at, plus one place of uncertainty. That's what we call the last sig fig, or the guess position. So if you were measuring an object against a scale that only was marked off in units of ones, 1, 2, 3, for example, we know for sure that this object falls between 2 and 3. And we are called upon by the rules of scientific measurement to give our best guess as to what it might be. I might guess 5, 2.5. You might guess 2.4, 2.6. What you specifically guess, the 4, the 5, or the 6, is unimportant. What's important is that you've correctly reported this measurement given this scale that only allows you to know for sure the ones place of your measurement, and then you have guessed at the tenths place. All measurements in science contain one and only one uncertain place. So if we report a measurement as 8.42 centimeters, I know, working backwards, that this 2 was the guess position, and that the 8 and the 4 are known with certainty. Okay? So when you see a measurement, you can understand that the last digit reported is always the guessed value, and all the preceding digits are known values. The only numbers that are tricky are zeros. Zeros are not significant if they hold place. So when zeros make numbers really, really large, like saying you measured 27,000, the chances are pretty good that these zeros are simply a rounding. They're not actually measured value. Or small numbers like 0.0045. Again, these zeros were likely not measured on the scale, but rather are simply there to show you how large or small the number is. So I would say that this first number has 2 sig figs, the 2 and the 7, and this last number also has 2 sig figs, significant figures, the 4 and the 5. That information is going to come in pretty handy for the calculation work that we do today, also as part of your first pre-lab question. That should help you identify the answers to that question. All right? And this idea is also addressed in the second pre-lab question, correctly measuring using measuring devices. Okay? When we combine numbers with different numbers of significant figures, the most common calculation we'll be doing today is multiplication. And so when we multiply different values, the answer to a multiplication has the same number of sig figs as the value in the calculation with the fewest sig figs. This rule prevents us from making up, supposedly, extra certainty in a value. So if we were to take a number like 228.4 and multiply it by another value like, let's say, 7.1. This has 4 sig figs, and our second value has only 2 sig figs. So our answer is only going to be allowed to have 2 sig figs. So my calculator, which has no idea about the rules of significant figures, tells me the answer of this is 1,621.64. This 6, first 6, is the last significant figure now, because it, according to the rules of multiplication, is where the uncertainty now lies. So I have to round this to 1,600, and I want my answer to be the same size, roughly, before and after rounding. So please don't make the mistake of rounding this to just 16. It's got to be on the same scale. 1,621 rounded to 1,600. And so we'll use that rule quite a bit as part of the exercise that you're doing today. Now, I didn't have any units on these values, but if I did, if I came back now and said, well, if this was a distance in meters, and this was also a distance in meters, my answer would have units of meters squared. So this would be an area that I would have calculated. All right? So we just multiply the units that way. So today, you're going to conduct a variety of measurements using a few different tools. This is one of the tools that you'll use. It's a meter stick, obviously, but it has 4 unique sides on it, which we've labeled for you A, B, C, and D. Each side has a different scale on it, different numbers of markings. All right? The side that's A has no markings on it at all. So if I use side A to measure the width of my table right here, I have no ability to know how long it is except between 0 and 1 meter. So the best that I can do is say that this is, I can mentally decide, is this ending at 1? Is it ending at, 1.0? Is it ending at 0.9? I can only have that one place of uncertainty. 0.9 is probably my best guess here. Side B has the tenths of the meter marked off. It's still relative to a meter, but now the tenths are marked. So now I can clearly see that the table falls between 0.9 and 1, and I am called upon by the rules of scientific measurement to guess, all right, and estimate, well, where between 0.9 and 1? So maybe I would say 0.94. Maybe you think it's 0.95. Again, what number we specifically pick as the guess, that's up to each of us as an individual interpreting the scale. But we have to guess in that second position. We have to, according to the rules. And on and on. Our ruler has then side C marked in centimeters, so the hundredths, and then finally side D marked in millimeters. So in today's lab, you'll use the ruler to measure different devices and see how you have to report the exact same distance differently, all right, with different numbers of sig figs based on the scale that you use to measure it. And so it's frustrating in science, maybe you've picked this up, measuring this table with the whole meter when I could measure it with the millimeters to get a much more accurate value. This helps us decide in scientific experiments what types of tools to use, all right, so that we can get the right amount of accuracy in our results. Another tool that you use today is called the caliper. I have an example of it right here. A caliper is used. Sorry about that. The video camera that I work with accidentally shut off. That'll happen occasionally. You'll see me step out and step right back into the frame and get restarted. So I just introduced the caliper, one of the other tools we'll use for making length measurements in lab today. If you've never worked with a caliper, it can look a little bit intimidating at the start. This caliper is a lot like American rulers that you might have encountered in school in that it has both a centimeters and an inches scale on it. We'll be using the centimeter scale only, which is the bottom. The way you use a caliper is by placing it around the device that you're about to measure, and then you squeeze, you roll the little ball, the wheel at the bottom, until you have a nice snug fit on the width of your device. So I'm trying to measure the width of my ruler here. And then you look inside the window that we have here. So let me show you how the window works. So inside the window, I'm seeing the centimeter scale on the bottom, marked off 2, 3, and the tenths of the centimeter are marked as well. Now there's a separate scale outside the window on the bottom, and that scale has also 10 lines on it. Okay? And where the first line falls shows you where inside the window your first two values come from. So my first line is clearly at 2, and it's at 2.0. My guess on the caliper is now going to be in the hundredths position. And the way we come up with the hundredths position is by finding which line from the outer set matches a line from the inner set that we are looking at. So it takes a little bit of practice here, but I think that my second line in my little window here, these aren't, maybe I haven't drawn the scale the best, but my second line seems to perfectly line up with a line from the upper set. Now it's the second line down here, so it's 0, 2. All right. The fact that it's the third line up here has nothing to do with our measurement. It's which line from this scale. This scale is measuring the hundredths of a centimeter. All right. So your first two values come from inside the window, and your third value comes from outside. So your calipers will be measuring in centimeters to the hundredths of a centimeter when you use them. Some of the other tools that we'll have today, real quickly I'll remind you, the meter stick, it's going to vary depending on which side you use, how many digits you're going to report. You'll use a graduated cylinder in lab today. The graduated cylinder will be marked with single volume values. So it would be marked in like 5, 6, and so you read the graduated cylinder up, and I would have to estimate, in this case, the tenths of the milliliter. So perhaps I would say in this case it's 5.5. All right. So for the graduated cylinder, you should, assuming it's marked in whole milliliters, you would guess in the tenths position. The Buret, which you may recall from your equipment exercise, looks like this. The Buret is quite different from the graduated cylinder because it measures down. Its volumes are reported by measuring downward, and the Buret is marked off in tenths of a milliliter. So if this was 24 and this was 25, we would also have the tenths marked on this scale. And our volume needs to be read in a downward direction. Now liquids in the Buret will always have a curvature to them, the meniscus. So here we have to estimate, all right, I think that this is 24, because I read it down, 24.12, so 24.2, and then I'll guess that last position. It's pretty close to 24.3, so maybe you'd want to guess 9 or 8. But you're going to have 2 digits after the decimal point for every value from your Buret, as you can see right here. 2 digits, so the hundredths of a milliliter. The electronic balance takes out all the guesswork from our use of it because it is programmed to formulate the best guess of the mass of an object. And it should report 3 decimal places, so you want to record all 3 of those, even if there's zeros in your value. So there's really no guesswork involved with using the electronic balance. Of important note, though, for the electronic balance is that it's always zeroed before you place an object on it. So there's a button that clearly says 0 or tare on every electronic balance. You hit that, you pause for a second until you see it reading all zeros, then you place your object to be weighed on the balance. So we're going to have different tools which lead to different numbers of significant figures, which we're then going to combine in a series of calculations today. 3 stations of work are part of the exercise today. In the first station, you will measure length. You will measure length of 3-dimensional objects. So really you'll measure length, width, and height. Those will be the measurements, and then the calculations you'll perform will be volume calculations. At the second station, you'll work with solid objects again. You'll be attempting to determine their densities. So you'll need the length, width, and height of the objects, just like you had at the first station, but now you'll also need the electronic balance to come up with the mass. Having the mass and the calculated volume, you can come up with the density of those objects. The third station will also have you calculate densities, but it will be for liquids that you will measure their volumes either using the graduated cylinder or the Buret. You'll use both for comparison purposes, and then you'll measure the mass using the electronic balance. So the idea is to measure the same object with the different tools, just like I measured the width of the desk with the different sides of the ruler a few minutes ago, and to understand that the choice of tools is very important to the accuracy that we have in the answer that we're trying to derive from our work in the lab. All right, so a quick overview to remind you, to help you with the pre-lab question. The significant figures of any measurement are the values of certainty plus 1 guess, or 1 place of uncertainty. So when we see numbers, all the values are usually the sig figs. The only thing we have to worry about, though, are zeros that might be placeholders. So we ignore those zeros. When we perform a measurement on a scale, we always have to guess at the last position by dividing the region between the last two markings into 10 places mentally and estimating how many places are taken up by our object. Okay? And finally, when we combine numbers, which I've erased, remember that a multiplied or divided value, the calculations you'll be doing in lab today, the answer has the same number of significant figures as the value in the calculation with the fewest sig figs. In our example, we took a number with 4 or 5 sig figs times a number with just 2, and our answer had to be rounded so it had only 2 significant figures. So that wraps up the pre-lab for today. You should be all set to quickly make your way through the 3 stations. Next week, when you see me, we'll be getting ready to discuss density, which is a 2-part experiment. 1 week we'll collect our data, and the second week we'll analyze that data to determine the densities of some solid rubber stoppers, using perhaps a method that you haven't seen before for measuring densities. So until that time, I wish you a good time in the lab. Take care and be safe in the lab. Have a good day.